Hello everybody, welcome back to the Gregorius Maths video. In this video, I'm going to be continuing on with the Homotopy theory series. And we're going to be looking at loop spaces and suspensions in what I anticipate will be a slightly shorter video, but it's going to be a very crucial video because even outside of the first 5 or 6 videos, which are slightly more basic machinery, the loop spaces and the suspensions are still going to be used heavily throughout the entire series. So we're going to talk about what they are, how they relate to homotopy theory, and a little bit about what happens when you do the loop space of the suspension of some space, and what the homology of the thing is. So, alright, so I'm actually going to give some motivation first for the definitions. So, we're going to actually take a look at some category theory to start off with. So, firstly, a based space, X, is the same thing as a space X along with a map from the base point to the space. So, what we do is, so the wedge product is a push out. So, we have two maps, like so, and then we have X, wedge, Y, like so. So it's the following push out. Now, what this means is that in based spaces, base point preserving maps X to Z and Y to Z is the same as having a map from X, wedge, Y to Z. So, in other words, it's the wedge product is the co-product in the category of base topological spaces. Now, okay, so with this in mind, recall the following statement. So, we have the Hom product adjunction. And it looks like this. So in set, we have Hom set of X cross Y, Z, being in bijection with Y, Z to the X, like so. So we have this bijection here. Now this transfers nicely down to top, where we put appropriate topologies on all of the spaces, and we get Homotop X cross Y, Z. So these are continuous maps between the two spaces, is in bijection with continuous maps between Y and Z to the X. Now, the final step we would like to complete is how to get this down to based spaces. So, we want a Hom product adjunction, but in the category of based topological spaces. Therefore, okay, so firstly, we'll define f of xy is the subset of this space y to the x along with the subspace topology, and it's a based space. So it consists of based maps between x and y, and the constant based, and they're continuous maps of course, and the constant based map is the base point of this space. So it's a space of base functions. And okay, so what we want is, we want all of our maps y from y to f of x, z. So we want them to be, so let's say we have a function f between y and f of xz. Now, for this adjunction to be true, remember that all of our maps must be based. So, firstly, we should have fy0 of any x being equal to z0. Okay, so at the base point in y, the function is constant. Also, we have the fy of x0 is equal to z0. So it's also constant at the base point in x, no matter what y we pick. So, what this is saying is, f is constant, f is constant on the following union, x cross x0, union y cross y0. Like so. And so, the adjunction will become hom top star of y f of x z is in bijection with, and now we'll have x cross y modulo this stuff, or in other words, x cross y modulo the wedge product. So, basically, when in doubt, modulo the shit. So we'll have hom top star of x cross y mod x wedge y, and then we'll have z. Now, this thing here has a precise definition, and there's a very special case too, which is going to be the main focus of the video. So, firstly, let's recap what we did here. So, we have this bijection in the category of sets. That easily transfers down to the category of topological spaces, but we want a similar adjunction, but for base topological spaces. This requires a little bit of work, but after a while we got it down to this adjunction here. Now, let's focus on this thing right here. And in fact, we'll make a definition for it. So, recall the Smash Product song, because it's very relevant here. Smash product between x and y. Smash product, how is it defined? You do the Cartesian product, mod the wedge sum. Smash product, that's how it's defined. So, let's replace this right here with this notation here. So, this is precisely equal to hom top star of x smash y z. So, there are a few special cases of both this function space and this smash product that will be of great importance in this video. Most importantly, what we want to note is the following. Let's see, we'll do it in blue. Okay, so, firstly, let's just take the following for granted. Sn smash S1 is homeomorphic to Sn plus 1. So when you smash the n sphere with the circle, you get the n plus 1 sphere. So, this fact right here implies the following. We have that pi n of f of S1 x is isomorphic to pi n plus 1 of x. Now, this follows from this adjunction right here. Why? Well, we have that. So firstly, we have that f of. We have that. So firstly, the important thing to note is that pi 0 of f of xy is equal to the set of homotopy losses of maps, based homotopy losses of maps between x and y. So from here, this is how it goes. F of Sn smash S1. Sorry. F of Sn smash S1 y is isomorphic to f of, and what we have here is Sn f of S1 y, like so. So we have this adjunction like so. Now we pass down to pi 0. So this now implies that the set of homotopy classes between Sn smash S1 becomes Sn plus 1 and y, and base homotopy class maps, is isomorphic to, passing down to pi 0, we get homotopy class maps between Sn and f of S1 y. Now, by definition, this means that pi n plus 1 of y is isomorphic to pi n of f of S1 y. And so, because of this fact, we give special name to both this thing right here and this f of S1 y. So, what's the name that we give this? Are the following definitions are in order. We have that the suspension of x is equal to x smash S1, and we have that the loop space of x is equal to f of S1 y. So this theorem right here is basically saying that pi n of the loop space of x is isomorphic to pi n plus 1 of x. Also, what this result here means is that we have an adjunction between the suspension and the loop space, like so, in the category of based topological spaces. So, what have we actually done here so far? So, I've defined the main two objects that we're going to be talking about in this video. That is the loop space and the suspension. But how did we get there? Well, firstly, we desired a based analog of this adjunction here. And we got it down to this thing right here. So we had to quotient out by some wedge product, which is the co-product in the based category-based topological spaces. And we got down to this adjunction here. Now, using some clever thinking, we managed to get this fact here. And that was just by using this adjunction which we worked for. So we gave special names to this smash product here and this function space here. And so we got this result here. That is that the nth homotopy group of the loop space of some space x is isomorphic to the n plus 1 homotopy group of x. And that's going to be an important fact that we're going to use quite a lot. Now these loop spaces also have a connection to they have a connection to Eilenberg-MacLane spaces. For any group G, we have that the loop space of K of G n is homotopy equivalent to K of G n minus 1. So it's not a proof, but sanity check. Let's apply pi n minus 1 on both sides. So they're going to have identical homotopy groups as the claim. Well, pi n minus 1 of the loop space of K of G n is equal to pi n of K of G n, which is equal to G. But this is all equal to pi n minus 1 of K of G n minus 1. So that's the sanity check that we need. So actually, and of course all of the other homotopy groups will be trivial by definition. But also, what's fun about this is that, what is fun about this? Oh yeah, remember that K of Z1 is the circle, and K of Z2 is CP infinity. So, this result here directly implies as a corollary, that the loop space of CP infinity is homotopy equivalent to the circle, as like so. So that's just a nice corollary that we get directly from talking about loop spaces. And now lastly, what I'm going to do is I'm going to talk about a model for the loop space of the suspension of some space X. Now, iterated loop spaces and, loop spaces of suspensions of spaces can get quite wild. But this is not too bad. So, we're going to show that this is homotopy. Actually, we're not going to show, but we're going to go through what this space is homotopy equivalent to, and what the homology of it is under some very mild assumptions about X and the coefficients ring. So, this is homotopy equivalent to the James reduced product of X. Now, I'm going to explain what that is, of course. But it's quite nice that we have such a thing. So what is the James reduced product of X? Well, definition. Let's form the disjoint union for all k greater than or equal to 1 of x to the k, that is just k copies of x. So we have this disjoint union, and then we're going to modulo by some equivalence relation, where you identify x1 xi xk with x1 and then we miss out xi, and then you just keep going until xk. Okay, don't worry. Where xi, what is xi? Chosen base point. Alright. So, this new quotient space is a CW cell complex. And why is it a complex? Well, of course you can form the space, Jm for x, and this is just consisting of tuples x1 up until xk, where k is less than or equal to m. And of course there are natural inclusions, Jm of x, including into Jm plus 1 x. And these are as subcomplexes. Now, since J of x, I might as well write this out. since J of x is the union of all of these subcomplexes, it itself is a CW subcomplex. And yeah, okay, so what we're going to do now is we're going to define a map between this construction here and the loop space of this suspension, blah blah blah. So we'll define lambda from J of x to omega sigma to the loop space of the suspension of x as follows. So it will map x1 up until xk to lambda x1 up until lambda of xk as the product of loops. Alright, this is good, this is good, this is good. But remember that we're quotienting out by this equivalence relation. So we need for this base point to kind of disappear when we do the product of loops. And so what you do is take the time for each loop to what you do is you take the time for each loop to what you do is you take the time it takes for each loop to traverse you make the distance between each xi and the base point equal to the time it takes each loop to traverse. And this map lambda is a homotopy equivalence. Now, the last thing I want to point out is that the following result. And as a corollary, you can compute the homology of the loop space of the sphere. So, theorem. And I think this is known as the Bott-Samuelson theorem. So we need R to be a PID. These are just mild assumptions. And we need that, we need that the homology of X with coefficients in R is torsion free. Then we have that H star, so the homology of the loop space of the suspension of X with coefficients in R is isomorphic to T of the reduced homology of X with coefficients in R, where this T denotes the tensor algebra. So, as a corollary, we have that the homology of the loop space of the sphere, which is not immediately obvious by any means, this is isomorphic to T of X, where the degree of X is equal to n minus 1. So, after this work, we managed to compute the homology of the loop space of the sphere. And this just off the top of my head, so I'm probably wrong about this, but there are some more recent results, I believe, about decomposing this suspension of the loop space of the suspension of X. I think it's called the James splitting, and I read about this before I typed up these notes, so I might be misremembering, but it just came to my head to maybe mention at the end of this video. I think it's homotopy equivalent to the wedge, overall n greater than or equal to 0, of the suspension of X smashed with itself n times. Now again, do not believe this for a second. I would definitely look up James splitting, and I'll correct myself in the description, because I'll look it up right away. But it's something like this. I know there is a model for this thing too, which is some kind of weird wedge product of a bunch of stuff. But I thought that was just worth mentioning. So, this video is meant to just clear up a lot of the terminology that I've been using vis-a-vis loop spaces and suspensions, and proving a few results about them, talking about a little bit of motivation coming from category theory, and most importantly, we showed this result here, which will be used quite a lot. So yeah, thank you guys for watching, and I'll see you in the next video. Goodbye.